Good morning. I'm Mark Maggiali from IIT, and in particular I come from ICAP Tech. There is a new facility that has been born from October 1st this year, and we have as a mission the continues the development of the ICAP and R1 platforms, and to support the research lines that are using ICAP in IIT. We have 7 research lines working on it, and also the community that is based on there are more than 40 ICAPs around Europe and around the world. So we need to help them on the software side, on the hardware side, and collaborate with them. But also we have industrial projects because we want to exploit the technology that we develop for our robots to, let's say, to more industrial projects with companies that are not research institutes or labs. Those are the people that are in the ICAP Tech. So I'm the facility coordinator. There are 8 people that helps me a lot on the organization and on the projects that we are carried on. And then there is a team of almost 30 people, like engineers, software developers, and technicians that were working on different projects, plus support assistance for system matter. So just few words about the organization, that we move from a standard, let's say, waterfall approach. So a mechatronics project was when we started working with ICAP or developing ICAP, there was a mechanical team, then electronics team, software developers, and it was like waterfall approach. So we first do mechanics, then we go for adding some electronics, and then do some firmware, software, and so on and so forth. We decided to change completely the schema, and we go from silos to transversal teams. So the difference is that the silos are still there. So of course there are people that there are heads of for each silos that provide the guidelines to how to design, for example, the mechanics, how to design the electronics. So we have a common way to do design of mechatronic things, but we have transversal teams where there is a mechanical designer, there's an electronic designer, firmware one, and we cooperate along the project starting from the beginning. So it's not a waterfall approach, but it's more an agile way to do things. And this is again another picture with the name of the team, and also the another very important figure that is a system architect, that is Ugo Pattacini here. That is important because in order to have a more coherent way to carry on projects, we need someone that give us the technology, the right technologies to do that, the right tools, help us to be coherent within teams, within the different teams. And this is how we collaborate with research lines. So there's inputs from research lines. They want to do a new gripper, they want to do a new part of the robot, and then what we can do is just take from them the requirements and start working on it within one team or 2 teams. But we do prefer to go in this direction, where a researcher give us, I don't know, usually 50% of its time working together within the team for 3 months on the specific project that he wants to realize. So that instead of having something deliver after 3 months, that maybe is exactly what they ask for, or maybe is something that is completely different from what they were have in mind, we can start since from the beginning to work together and go together to the end of the project with something that is more suitable for them. So related to the platform, and then I leave the floor to Ugo that is going to be more technical and specific. I want to just give you a few details about the hardware. So what we provide for a TERRINet is HiCab. HiCab is a humanoid robot with 56 degrees of freedom, brushless motors and DC motors for the hands and for the head, and brushless motor for legs and upper body. It weighs about 30 kilograms. We have a 6-axis force torque sensor in the legs and in the shoulders. We have, and this is kind of unique, 4,000 taxels, so all over the body. We have almost like 50 IMUs and stereo cameras, and plus, of course, other sensor encoders and standard things. So this is a map. So we have iCabs almost everywhere. So it's, I mean, as you may understand, it's quite complicated to deal with all the possible issue that can rise with a platform that is, I mean, it's still a prototype, right? It's not a product. This is just few things about the skin. The skin is capacitive based, so this is the principle is very simple. There is a soft material here that and then there is also a soft die ground plane on top of it. So the more you press, the more the capacitance increases, and then you can get the pressure. So we have 8 bits analog output that is converted within each triangles, and so we can get all this information through CAN buses connected to other Ethernet gateway, and we can collect the whole tactile image of the robot every 50 milliseconds. So those are more in detail what we have in the robot. I will not go into detail, but I mean, I leave the. If you are interested, we can go deep, but I just go through. What I want to show you is just the architecture, just to give you a brief idea. So we have an Ethernet backbone. So this is the i7 PC on the embedded PC and the head. Then there's an Ethernet connection that goes all around the robot, and then we have CAN buses lines for skin electronics, or for FT sensor, or for brushless motor cards, motor control cards, and all, I mean, every boards, this EMS is like a gateway, but it's not only a gateway because it can also do some control loops. Like specifically, we have, this is the head that can run loops at 1K or 100 Hertz, and then there's a Wi-Fi connection or gigabit connection to a cluster of PC, GPU, whatever. And we have an internal 100 megabit Ethernet with a custom protocol, and then those cards. The first one is for controlling brushless motor. So here we close the position and velocity and torque loop, and in the 2FOC we do the field-oriented control of up to brushless motor, and we can have also current control loop at 20K. So those are the sensor that we have. So we have rotor position, and then also joint absolute position, and we do not have torque sensor in each joint, but we use six-axis force-torque sensor to retrieve the torque from the motor, and we have also, of course, current sensors. And for the MC4 Plus, this card is controlling directly for DC brushless motor that is connected directly to Ethernet. There's no CAN buses in between, and the principle is the same. We have two measurements, one from the rotor that is good for retrieving the velocity of the joint, and one for having the absolute positions of the joint afterward. And this is R1, that is a completely different robot that is made for service robotics. Does not have legs, but has two wheels. It can extend its body to reach something on a shelf, or going down for grab object from the floor, even if, to be honest, it's quite difficult to get object from the floor because you don't see it. There are 28 degrees of freedom, so much less, and mainly is because there are no legs. In fact, the arms have 80 degrees of freedom because there are the classical 7 degrees of freedom plus the extension of the forearm. There's a bigger battery. We have the payload is not that high, and we have it weighs 54 kilograms. And the sensor we have are, standard. We have an embedded PC on the base, plus two Jetson Tegra X2, one for controlling the two standard stereo cameras, USB 3, and one RGBD that is the RealSense camera. Then we have a system on chip on a head that is controlling the LIDs, the metrics of LIDs for the face. It's controlling for speakers, for microphones, for beamforming and speaker, and there are also laser on the front and on the back of the base, and there is also Wi-Fi connection to the external world, or Ethernet connection as well. And this is the schema of all the motor control cards that are embedded in the robot. Okay, this is another picture where there are more specifically describe the sensor we have in the robot. And this is the last slide, that is just a video on the robot. This is a future possible scenario where the robot is go and grab you see the extension of the arm. I can grab a glass in this case and bring it to the lady. So of course this is as you know that this is just a spot, but that's the idea. So if you have question, otherwise we can continue with Ugo's presentation that is more technical and goes more in the request from Philippe. Yes, we sell it as well. It costs less than the iCab because it's of course it's less complicated, and the parts are not as expensive as for example, it does not have harmonic drives as a gearbox. So yes, how much is cost? Okay, it's it's like something like 120K. So it's not cheap. Of course, it's not that cheap, but it's half the price of the iCab. And we, since we are a research institute, we don't have markup on top of it. So we just cover the costs for building it, for maintaining it, and construct it, and all the assembly cost, and that's all. We have 3 R1 around from now. Yes, I mean this was just a general one, but Ugo will provide you a more, let's say, insight on the software part.